ANCAR also features a beamline for protein crystallography. This is used to characterize the structure of macromolecules, the most important subgroup of which are proteins. These studies are conducted by means of an arrangement comprising an X-ray mirror and silicon crystals, which filters out of the broad spectrum of electromagnetic radiation offered by the storage ring X-ray light of a defined wavelength, concentrating it into a focus of fractions of a millimeter in size. In this arrangement there is also a small crystal of the sample material positioned on a goniometer head. This diffracts the X-ray light coming from the beamline in a way characteristic of the internal structure of the crystal. A two-dimensional detector registers the radiation diffracted by the sample crystal. This measurement is repeated several times for different crystal orientations. In each of these hundreds of detection steps, the crystal is turned a small step further by means of the goniometer, so that a complete picture of the radiation distribution over the entire space, as generated by the crystal, is obtained in the end. To prepare the measurement, the crystallographer first mounts the crystal under a microscope onto the tip of a goniometer head and then places the head on the goniometer. Subsequently, the sample crystal is aligned with respect to its position relative to the beam by means of a microscope camera. To avoid radiation damage, the crystal is frozen and kept at a temperature not much above the boiling point of nitrogen by means of a cold gas flow. The next step is data capture. After each frame, the image disk of the detector is scanned by a laser beam, reading the data as from a compact disc. Then the disc is erased by exposure to powerful halogen light. In this way, the X-ray diffraction data just collected are to be used to determine the coordinates of the hundreds or thousands of atoms in a unit cell of a protein single crystal, and in this way obtain the complete three-dimensional structure of the protein molecule. Sophisticated computer codes implementing complicated mathematical formalisms support crystallographers in this job. However, this is not sufficient to do the job. The field of X-ray waves diffracted by the crystal contains the information about the three-dimensional structure of the protein molecule in two components, namely intensity and phase. Only the intensity can be measured directly by the detector, while the phase must be reconstructed in a suitable way for the structural solution. In ANCAR, the rather modern multiple anomalous dispersion, or MAD, process is used for this purpose. It exploits the fact that, unlike conventional sources, the ANCAR protein crystallography beamline allows the wavelength of the radiation impacting on the sample to be set at random within wide limits by means of the silicon crystals. In this way, certain heavy atoms incorporated in the crystal structure can be excited into resonance and then indicate their position by a change in their scattering power, in this way allowing the phase to be determined. Unlike conventional methods, the MAD method in principle offers a complete solution of the structure, even if only one single crystal of the substance to be studied is available. This used to require a series of experiments with a large number of samples prepared in different ways, an expensive process of trial and error. Other advantages compared to structural studies by means of X-ray tubes are the higher intensity by roughly 2 orders of magnitude and the resultant shorter exposure times, the small divergence, and the spectral purity of the radiation from the ANCAR protein crystallography beamline.